This lecture focuses on gravitational potential energy. It says, Jackass the movie is great. I think it's the tradition of physical comedy, which I'm really interested in. It's the relationship to gravity and how gravity acts on the body, and that's going to be what we're looking at here. So gravitational potential energy. Number one, students should understand the factors that affect gravitational potential energy. You should be able to calculate gravitational potential energy and any of the factors that are involved in figuring out gravitational potential energy. You should also be able to relate gravitational potential energy to work and power, and once again relate it to the law of conservation of energy. So potential energy. Gravitational potential, there are actually multiple types of potential energy that are due to the position of an object. Now, you can have potential energy that's due to position in a gravitational field. You can have potential energy that's due to the position in an electric field, or that's in the position of a temporary deformation of an elastic spring, or ball, or anything that can stretch. So those are the multiple types of potential energy that there are, but we're specifically interested in gravitational energy. Now, this is the formula for the star chart. It says PE and then a little g. This is a little subscript that lets me know that this is the potential energy of gravity, is equal to mgh, where m stands for the mass of the object, g stands for the gravitational pull or the acceleration due to gravity on the surface of that planet, and h stands for the height above the surface. So this is considered to be the energy that the object can gain as it falls. So if you have an object that's has 100 joules of potential, well, when it falls to the ground, it should have 100 joules of kinetic, which we'll talk about later when we talk about conservation of energy. It is very important that mass be in kilograms and that the height be in meters, so that you should get your standard unit of the joule. Alright, this question says, which point has the most potential energy? Remember, the formula that we have for potential energy is mass times gravity times height. Now, on the roller coaster, we can assume that the mass of the roller coaster is not going to change as you go through it, unless somebody falls out, but that would be really bad. So we need to understand that the mass is going to be a constant number. We also know that the gravity is not going to change significantly. It is true that the further you get away from the surface of the Earth, the less gravity is, but that's a very, very, very insignificant number when we're talking about roller coasters. So if you take an example, if you're at sea level and if you're at the top of Mount Everest, the difference in gravity is less than 1/100 of 1 decimal. So it's a very, very small value, so we can assume that the g value is actually the same. So really the only factor that's going to be determining how much potential energy an object has is the height. So you want to have a high height for a high potential energy. So the point that's going to have the most potential energy is going to be the one that's physically the highest, and in this case it would be B, followed by C, followed by A, and then followed by D. So we could rank those and say B is greater than C, which is greater than A, which is greater than D. Okay, this question says, which object has the least gravitational potential energy? So the same reasoning works that we did on the previous one. We can assume that the mass and gravity remain constant, and so really what we're looking for is the one that has the least amount of height. A lot of people take a look at this and they say, oh, well, B, because it's losing potential energy. That's not the case. Whenever it has the least potential energy is when the height is the lowest, and that would be at C. This question says, calculate the potential energy of an object with a mass of 10 kilograms that is 3 meters above the surface of the Earth. So we draw it out. We say we have an object that is 3 meters above the surface of the Earth. It is 10 kilograms, and we are looking for the GPE, the gravitational potential energy. So now we take a look and we say, okay, the formula that we have for potential energy is GPE equals mgh. We know the mass value is 10 kilograms. We know the gravity on Earth, which we are going to assume is where it is 9.8 meters per second squared. And we know the height is 3 meters. So in order to calculate the potential energy, we would just say mass times gravity
times height. We would multiply 3 times 9.8 times 10, and as a result we get 294 joules. The units check out because on one side we have a joule, which is a kilogram meter squared per second squared, and on the other side we have kilograms multiplied by meters per second squared multiplied by meters. So if you look, kilograms, kilograms, second squared, and then meters times meters, which is going to be meters squared. This question says, determine the gravity on a planet that when an object with a mass of 5 kilograms is 10 meters above the surface, the resulting potential is 128 joules. So let's go ahead and draw it just to see what's going on. We have an object that is 10 meters above the surface of the Earth, or excuse me, the surface of the planet. We can't assume that it's Earth anymore because it says determine the gravity on a planet. So we know we're no longer talking about Earth. We know that the object is 5 kilograms and it's 10 meters above the surface of the Earth. So we can say we are trying to solve for G. Now a lot of people have issues with that because they say, well, G is always 9.8. Remember, G is 9.8 on the Earth and on the Earth only. So we have GPE equals mgh. We have the mass as 5 kilograms. We have the height that's 10 meters. And we have the potential energy as 128 joules. So what we do is we say GPE equals mgh, and what we do is we divide both sides in order to solve for G by mh. When we divide both sides by mh, it cancels out, leaves us the G term, and so we have G is equal to GPE divided by mh. In our case, that would be 128 divided by 5 and 10. Remember, when we're putting this in the calculator, we want to make sure we do this first. And when we do that, we get 128 divided by 50, and you get 2.56. Now this is G, so we should be measuring this as meters per second squared. Now we do want to make sure that that value is actually correct, so we look at our units. We say, okay, the joule, remember, is a kilogram meters squared per second squared. And we divided it by mass, which is kilograms, and height, which is meters. So, kilograms cancels out, meters cancels with the squared term, and what I'm left with is meters per second squared, which is what I want it to be.
So vertical work in GPE, what you should realize is if you take the work equation, which is force times distance, and instead of using the force part, you use the equation for weight, which is mass times gravity, you actually get the GPE formula. So really vertical work and GPE, they're the same formula because it's conservation of energy. Any work that you do in lifting an object to a certain height is going to equal to the potential energy that it has to fall back down that height. That's conservation of energy relating vertical work and GPE.
This question asks us to take a look at the graphical relationship between mass and potential energy due to gravity. And whenever we do this, we say PEG is equal to mgh. Now, whenever you're looking at the graphical relationship between variables, remember that you isolate those variables. So I'm looking at mass and potential energy. Everything else goes away because it's said to be held constant. So really what I have is PEG equals m. We substitute in, we say y equals x, and then we graph it. We say, okay, if we didn't know what a y equals x graph looks like, we graph it, and we get this relationship here. Now remember, even though we get a graph that looks like this on the calculator, this right here has no relevance because we're not going to have a negative mass. So really, the only correct answer in terms of the graph would be the positive quadrant right here that shows a linear relationship going upwards, where we have mass and we have PEG. All right, this question says a weightlifter bench presses 200 pounds, a distance of 1.2 meters, 22 times. How much work does he do? So they are lifting a weight that is 200 pounds, and they lifted a total distance of 1.2 meters. Now they do that 22 times. So whatever we determine is the work for one time, we have to multiply it by 22 because that's how many times they're doing. Now the question says, how much work does he do? Now, when we're talking about work, we have to realize that what we have here is vertical work. And remember, vertical work is equal to potential energy due to gravity, which is equal to mgh. So even though it says determine the work, we can actually solve for the potential energy that's gained, and we can do it that way. Now, remember when we did the work equation, work is force times distance, and force is mass and gravity, so it ends up being the same thing, but conservation of energy. So we are given a mass, and the mass that we are given is 200 pounds. Now we do realize that that's not going to fly because that's not a standard unit. So we need to convert that mass into the standard unit. And there are 2.2 pounds in 1 kilogram. If you didn't know it, you could look it up. And then you can say 200 divided by 2.2 gives us a mass of 90 kilograms. So now, once you take a look at that, you know also gravity. We're going to assume that this weightlifter is on Earth because that's where all the weightlifters we know are. And the height is 1.2 meters. So what we can say is we can say that the potential energy of gravity is equal to 90, well that's actually 90.9, times 9.8 times 1.2. So when we enter that in the calculator, 90.9 times 9.8 times 1.2, we get 106.9 joules. Now remember, that's not our final answer. Okay, what we did is we basically lifted this weight one time with 106.9 joules of energy. However, 22. Because of that, you've got to multiply this value by 22 to realize that it's actually 2,351.8 joules. So just to put that in perspective, people often want to compare weightlifting to cardiovascular exercise like jogging to see how much energy they burn. Remember, if we're going to convert this to some form of energy that we're used to, we can actually convert it into into calories by saying that there are 4,184 joules in a dietary calorie, which is a kilocalorie. So if we were to do that, we'd say, okay, divided by 4,184, it turns out that whenever you lift 200 pounds, the length of your arm, 22 times, you burn about almost 1 calorie. Not quite. Not half a calorie. Now, granted, there's also going to be some other things. The muscle's going to contract. You're actually going to use more energy than that because your body's not 100% efficient. But 0.56 calories to do weightlifting. Alright, this question says, an escalator moves a 100 kilogram man at 30 degrees above the horizontal for 30 meters. How much vertical work is done? So, you have an escalator that moves the man 30 meters at 30 degrees. So, we are trying to figure out the amount of vertical work done. So in order to figure out the vertical work, we obviously need to find this vertical component right here, which we're going to call the height, but is also known as y. I'm going to go ahead and put it as y for now, because y or h kind of gets confused with hypotenuse sometimes. So let's go ahead and just leave it as y for now, and we'll change it later when we look at the formula. So it says we are looking for vertical work done. We know that work can equal potential energy. And so since we know that, we can say that it's equal to mass times gravity times height. So if we can figure out what the height is, this question becomes really easy because we have a mass of 100. We know that all the escalators that we know of are on Earth. where gravity is 9.8. So once we figure out this term, it actually becomes very, very simple. You should remember this from earlier this year, that if you have one side of a triangle, you can solve for the other sides using either sine or cosine. Remember, sine is used to solve for the y component or the opposite side. Cosine is used to solve for the adjacent side or the x value. So in this case, I'm interested in the vertical. So what I would do is I would say that the height is equal to 30 times the sine of 30. Now when I do this calculation in my calculator, I do want to make sure that my calculator is in degree mode by hitting the mode button, making sure that degree is the function that's highlighted, not radian. And then I do 30 times the sine of 30. And I get 15. So my height is now 15. So the work, or potential energy due to gravity, is equal to 100 times 9.8 times 15. So once you do that, 100 times 9.8 times 15, and you get 14,700 joules of energy. Okay, the final example for this one says that we have a waterfall that the waterfall is a height of 100 meters and we have a flow of 1,000 kilograms per second. So 1,000 kilograms of water is quite a bit. How much energy is produced in 1 hour? So this would be the things like the Hoover Dam, and the water falls over the dam, turns a turbine, produces electricity. It's another example of the conservation of energy. What we were trying to figure out is the energy that is produced. So I'm just going to go ahead and say that it's potential energy right now. It could be work, it could be anything that we've talked about so far, but since this is potential energy, I've got a clue that it's going to be that. Now I also have potential energy is equal to mass, gravity, height. So what I have is 1,000 kilograms of water per second that flows over this waterfall that's 100 meters tall. So this may be confusing for some people because you've never seen kilograms per second, but it does say how much energy is produced in 1 hour. So you have a time, and that time value is 1 hour, which is 3,600 seconds. You should know that conversion by now. So if you have 1,000 kilograms every second, and you're doing it for 3,600 seconds, you should realize that just by multiplying those two together, you are going to get the total mass of water that goes over the cliff as being 3,600 times 1,000, which is 3,600,000 kilograms of water. Now you know that gravity, all the waterfalls that we know of are on Earth, so we know that the gravity is 9.8 meters per second squared. And we know that the height is 100 meters. So that allows us to figure out, we say, potential energy due to gravity is going to equal 3,600,000 times 9.8 times 100. When you do this calculation, you get 3,600,000 times 9.8 times 100, or 352800000 joules of energy. So 3,528,000,000 joules of energy, which is quite a bit from this waterfall.
So by now you should understand the factors that affect gravitational potential energy. Number 1 is mass. Number 2 is the acceleration due to gravity. Number 3 is the height. All three of those factors are equal. None is has more effect than the other. They are all directly related. So if you double the mass, you double the energy. If you double the height, you double the energy, and so forth. You should be able to calculate mass, gravity, height, or energy given the missing variable, or given enough information. You should be able to relate gravitational potential energy directly to work. We did that many times by saying that you have the vertical work and the GPE, they're the same thing. And then you should be able to relate that to power as well. What is the power of a weightlifter? How many how far can they lift the weight in a certain amount of time. And then you should also be able to say, okay, the reason why we can relate work and potential energy is once again the law of conservation of energy. It keeps popping up saying, okay, energy has to be conserved. It's got to be converted from one form to another. So if an object has gravitational potential energy, it had to get that energy somehow. Some sort of work had to be done to put it in that position.